My presentation will be in English because I have prepared for one conference that in English. So it is coupling or linking high performance HVAC, heat pumps, building integrated PV via smart grids and energy storage for zero CO2 emission healthy buildings. Design new and deep refurbishment of existing. I'm at the end maybe because I don't think that we engineers and also engineers and engineering science have to do and follow only what our governments and political groups are advising. They have prediction that we will reduce also use of fossil energy sources, but measures which they are supporting are absolutely not adequate. And those coefficients about heat transfer coefficient and so on, exactly we have to go always beyond. Copy-paste of project is also not bringing anything. So we have always to look just the building we have to improve. It is clear that we are at really at the edge of risk which is bringing weather extreme, more and more catastrophic events, fires, all part of the world, and in the same time also the results of different strange, some very bad political issues and decisions, too much concentration in cities and dying villages. Also naturally connected with political extremes, bringing migration, immigration. Renewable energy sources, use and related technologies are in research, in development. There are also manufacturing capacities in increase in the world, and implementation is not following what is exactly obtained and reached. Building integrated photovoltaic PV as a transparent PV glazing and use also as opaque layers, as a layer within the building. And we are able to construct, to renovate and construct new net zero energy houses, net zero energy building. What it means, net zero? It means that the building is exactly on the building production of electricity and surplus in certain period after really satisfying needs and battery charge are sent to the grid. In other periods, to the house is using electricity from the grid. When it is balanced between produced and used from the grid, zero at the annual level, then that is net zero building. And exactly, it is not impossible, and it is really possible. So, building envelope, integrated opaque and PV, semi-transparent, we have to have in mind and to try in our redesign, refurbishment, and new building design to reach. Solar decathlon Europe. There were three, 2010, 2012, and 14. And 2012-14, I was a member of jury. And you see, these are members, winners, Rome, and before in Grenoble. They are very simple buildings. And what was really fascinating is that all buildings were producing between, that was in 2012 and more, producing 2 to 4 times more electricity than they were using. Here is just an illustration what is the smart grid. Smart grid, it was Schneider microgrid in all these solar decathlons, and its role is to really control produced electricity at the building. If there is surplus, then it is to be sent and distributed among the neighborhood. And if after that is still surplus. Naturally, in buildings are full batteries for storage, but if still is some surplus, then it goes to the grid. So it clearly shows that it's easier to reach zero fossil energy settlement or neighborhood than just one building. Here, there's as I said, between 2 and 4 was production of electricity on this solar decathlon 2014. You see on the ordinate, the energy production, electricity, and down energy consumption. And those days in Paris, they were really not very sunny days, but solar radiation, and there was rain, and so, but still. And it was a result not of very special new, even not of today, quality and efficiency of photovoltaic, but excellent harmonization between building construction, thermal building features, HVAC, and use of PV. For example, here is some detail about PV glazed facade. You see window and PV glazed facade. And to get the highest efficiency of integrated photovoltaic, it is important to keep PV layer at the optimum temperature. That's approximately 25 degrees. So, for example, in summer regime, it is useful to have circulation of air between the PV glaze and the window, and to keep temperature at the level that is necessary. And the winter, this air could be used as a fresh air, for example, for preheating of ventilation air. It is naturally here is just given sketch of heat and transfer between different components of this wall. And here is what is important. So for determination of relevant features, properties of building integrated PV layer. So when it is integrated a layer within the building, it has to, for it is necessary to be determined all relevant features, like for all layers built into envelope structure. So here is measurement of solar heat gain coefficient. Naturally, here was a lot of talk today about demand and reconstruction and so on for heating and for cooling, and comparison about final results. Real optimization of building energy demand can be done only with all year-round building performance simulation. All year round with all these 8,760 hours. Because in that case, you will have the same structure in different conditions, winter and summer. Some excellent results for winter are peaking with energy need in the summer. So it is then also important how you do building performance simulation. When you use just building energy simulation, even that's Energy Blues or Transist or any other, your calculation goes with constant wall temperatures, and exactly their boundary layer is not such. So it is important, concerning very important impact of wind affecting the outside wall of the building, to use also co-simulation, computer CFD and building energy simulation. So here it is an example how it is developed as co-simulation program. I'm just showing you here are measurement results of developed co-simulation program. You see it is the temperature on just in the room based on just building energy simulation. And the other one, result of co-simulation, are these measured values and these red calculated values with the co-simulation. I'm showing this to outline that permanently engineers are to follow science and to do even in the design to implement the most current knowledge. it's really not, when you listen all these presentations about different balances and the calculation, it is so far away from what really to this day is possible. This is further the implementation of this CFD simulation with built-in energy efficiency and demonstration how it can be used not only outdoor. You start with windrows I have no time to go in details, I have really to run. Start from windows, get velocities on the outside wall, and then enter into the space. I will just review a few results showing of engineering design, how exactly can be really improved energy efficiency and implemented renewables. Deep energy refurbishment social housing in Belgrade. You see facade, ruined facade needs renovation. Also it is social, there are 90% of apartments have cooling, air conditioning. It is possible to reduce 5 times loads, and loads annual loads for heating and cooling. On this way, even you have here comparison, because this is red is naturally heating, and this is measurement of built with district heating, and it is cooling. So 5 times will be reduced load. If we only looking for this air conditioning, if we put this second facade, photovoltaic, it was shown by simulation, very detailed, that just a part of the building and a part of opaque, that only 1/3 of this surface of semi-transparent PV glazing would be enough to cover all needs to power these split units of air conditioning. And naturally, if that would be done, it could be even used of that electricity also when it is not necessary conditioning for other electrical needs. And even more, whole new Belgrade is on water. So those split units exactly can be changed or redesigned to become exactly in the function of heat pump. Naturally, again, real design should deserve that underground inlet and outlet of water from underground should be CFD simulated to be real and sure that will not disturb underground water temperature. It is easy to drill even on the sidewalk of the streets in Belgrade. Here is also, for this case, for example, for this building, just recently was in SMEITS journal, distributed mini heat pumps with shared ground loop, what could be perfect solution for this building when this reconstruction for implementation of BIPV and heat pumps will be implemented. This is about these directives, and we already heard in some presentation about first and then recast and second recast and so on, about goals to 2050. But when you read this final result of about EPBD from Brussels, final sentence is, but among the results discussed, nearly zero buildings and there are is written, and also there is also written as a result that overall most respondents consider they established a good framework for improving energy performance in buildings, and that it has raised awareness on energy consumption in buildings, giving it a more prominent role in energy policy. I mean, this kind of conclusion for such amount of money which was put into all these projects, but most of those projects in European were just for not even 8 centimeters, but even smaller thickness of layer as insulation to improve what is absolutely, I mean, nonsense, because it is very cheap to improve these thermal properties of envelope with thicker amounts of insulation. And exactly the thickness is to be determined so that loads, annual loads, full load, are to be minimized. So you have to try with different models of improvement till you minimize load. Also this zero, nearly zero for me, it's not engineering term. Cannot say nearly secure bridge, just. Others, a few examples, historic building in center Belgrade can be, it was reconstruction and necessary to get design because a deep change of use of building was the goal, and we made this implementing my way of doing energy renovation and implementing building performance simulation, and it came out. We worked with these 4 models and initial model, and it came out that it was even with very detailed calculation of different parts of HVAC system, and even drilling and all works, that implementing renewable, that it was cheaper than that just to do this, ordinary, adaptation of the building. Traditional Serbian building, analyzed using building performance simulation, that is ECO-SIM, Bentley software. It is not free of charge to buy. And this is interesting diagram I did find in our hydrometeorological institution in Belgrade, very illustrative, showing about the 4.54 degrees Celsius increase of temperature in the last 100 years. You can see length of period is on the ordinate, and down are years, and red colored areas are more and more bigger. There are models we are analyzing in this study, and here we have map of groundwater in Serbia. You see there big part of Serbia with very extensive water, and temperatures are given in, I'm running from that graph. The design of this redesign of this building, traditional with minimizing loads, brought us to zero fossil energy house. There was in design introduced heat pump, underground use, and PV used to power heat pump. And you can see on this graph, in this table, that these light blue colors are only period with the PV minimum, photovoltaic minimum, surface a little bit less, lower temperature than necessary, and road, a little bit darker red color shows surplus energy, so it could be sent to the grid. A little bit bigger area of PV maximum is exactly giving us energy plus building. So exactly installing these photovoltaic, renovating buildings in villages, in rural areas. And it's interesting that in Switzerland is permitted only to use and to put PV on buildings. So by distributing, renovating buildings, and naturally in this renovation the goal had not only to deal with energy, but to improve farmers' living standard in their houses. So they have to get the same quality of life like people have in cities, to have electricity, to have lighting fine, and to have IT and everything what is necessary. So that's the only way to keep them to proceed to live there. There is here is also the exhibition up. Very interesting example, historical example. It is even in Ashray Handbook. It was in '84 built 3.5 megawatt seawater heat pump assisted multi-purpose solar system in Budva. There were heat pumps produced in Belgrade, Frigostroj. There were solar collectors from Slovenia. And now that system is 35 years in operation. 35 years in operation. It is with solar collector surface is not covered green surface, but parking place. So it's very, very smart. And it was for heating sanitary water, and is still in its permanent maintenance in operation, and for air conditioning in summer, and heating within air conditioning in autumn and spring. Was paid back in 1.5 years. Here is the scheme, we cannot go in details. Now, geothermal. Geothermal is, and in all this presentation today, in some of them was mentioned that heat pump are using also geothermal. Exactly, it was first at Belgrade Faculty for Mining introduced new term, but also in Germany, and their standard they're using underground for heat. This underground or underground between to the depths 15 meters, 20 meters. There is very stable temperature all year round, and that is, so I said underground, it is sub-geothermal. So it is more and more used in the world for this kind of use of energy source for heat pump as sub-geothermal. And there are different kinds of underground use, heat pumps, ground water wells, ground heat exchangers, ground wells. There are borehole heat exchangers and so on. Energy piles are also using underground energy as a source, and are used also for non-residential buildings, and very interesting there has HVAC City Bratislava, we did participate in that consultation. Very famous is Zurich Airport. They have the 300 piles, and 85% of annual heating demand they are exactly covering by these piles. Naturally, with energy piles, there are also some other delicate problem because it's thermal also study about the impact of the change of temperatures of the piles. The most important question in implementation of renewable energy sources is the intermittency and changeable variability in their intensity. And energy storage is, because of that, very, very important and crucial for further development of large-scale utilization. So there are several systems. There is a perfect study in the National Renewable Energy Laboratory in Colorado, US, about high energy batteries, about pumped hydro storage, about compressed air energy storage, and natural, pretty more even before known thermal energy storage. There are different underground thermal energy storage concepts here we find in the paper. Underground thermal energy storage using aquifers, boreholes, and caverns. This is example also of aquifer thermal Utrecht, Netherlands, the large-scale borehole thermal energy system on the top of the storage, and on the top, on the surface, it can be used for this and so on. Something not very new, I mean here is very new, but in some countries in the world is implementation. Energy storage using closed or abandoned mines. Abandoned mines, and I mean closed mines. On the left you see mines. It can be energy mines, can be of mineral, of coal, or what different mine. And there are plenty, and it is potentially a great source which could be used in Serbia for increase of utilization of renewable energy sources. This is very old mine, and there are also this possibility. There is also museum of mining. So old coal mines can heat our homes again. There are experiences in UK, there are in Poland, there are in Canada, and some also in US. Solar energy technology current status, PV, fuel cells, wind turbines on Earth during the past several decades are currently in intensive growth. However, these technologies cannot provide enough electrical energy to satisfy demand enormously growing in first decades of 21st century. Similar technologies applied in extraterrestrial space exposed to the extraterrestrial solar radiation could provide quantitatively and qualitatively by the exergetic higher value, more reliable, sustainable energy to those Earth. Consequently, it is crucial for the world to research, develop, demonstrate, commercialize, and deploy more affordable and more sustainable solar energy utilization technology, solar space power generation. On that idea, there are very detailed plans about the use of extraterrestrial solar radiation and wireless transmission to Earth based on Nikola Tesla, research and even his lectures. Very detailed programs that are in Japan, Mitsubishi has it till 2020, and also in China they are developing. As a final comment, I would stress that in order to stop the global climate change, in addition to the interrupted our research and development aimed to advance solar building integrated PV, which is exactly the technology which made the biggest in history of technology decrease of cost from the early appearance to today. 11 times it is today cheaper. So heat pump with power by PV is absolutely today fully commercial and cost effective. To advance, beside the research and development, aim to advance solar building and other S technologies, it is necessary to find relevant circular economy-based schemes. So no wastes, today we have no wastes, or multi-sector complex system linkages for the sustainable earth resources, utilization, environmental protection, and or already damaged environment recovery. Interruptible availability and variable quality of most types of rest requires energy storage, large rest utilization need, large-scale storage system and large storage volumes. Worldwide, many abundant mines of coal or minerals offer large storage volumes almost ready-made to be used directly for energy storage. Using thermal energy from the environment, heat pumps are increasing energy exergy efficiency and contribute to the reduction of primary energy demand, particularly heat pumps use of the underground enable high efficiencies on an annual basis. So just that is, thank you, I was really in hurry jumping, and definitely all experience by real engineering is when you minimize the loads. To minimize the loads, all measures are exactly cheap. You go to the highest thickness of insulation and see if further is not bringing any more really reduction of loads, and then you will have much lower installed power of the highest quality of current HVAC system, of highest quality heat pumps and all other equipment. So equipment which is much more valuable in much higher costs and therefore is reduced. And you will get cost effective in Singapore, where electricity is very expensive, or in Dubai, or Russia, where electricity is cheap. Thank you very much for your attention.
Thank you.